Hey there, today we are going to talk about domain and range of functions. So first, let's start with the definition of domain and range. The domain is all the possible x values that you could plug into a function. Okay, we're looking up horizontally along the x-axis for these values, and if you're looking at the graph, it's just anywhere that the graph shows up along the x-axis. If you can go to an x value and then go up or down and find the graph, then that is part of the domain. When you're looking at the equation, then we're looking for real numbers. So anywhere where a function might be undefined or get imaginary numbers, and those are things that would not be in the domain. Now the range is the same thing, only for the y-axis. So these are all the outputs that I could get from plugging in the values that are in the domain. So in this example I see here on the right, it looks like at negative 5, 5 right here. This is where the graph ends. So anything less than negative 5 on the x-axis would not be part of the domain, and anything greater than 5 would not be part of the range. Now the arrow down here in the bottom right indicates that this goes on forever, so I can assume that my range starts at 5 and goes off to infinity, and that the domain starts at negative 5 and goes to infinity. Now, a lot of the time, domain and range are written as intervals, but sometimes you might have just a single point or a bunch of intervals stringed together using that union symbol. So let's look at some examples with this. Here I've got a rational function and a radical function, and we'll find the domain and range, and we'll look at the graphs as well to kind of connect all the dots on this. So first of all, with that rational equation, where a rational equation runs into trouble with domain is when the denominator is 0. I can't divide by 0, it's undefined. So anytime that I have an x value that will cause the denominator to be 0, that's something I'm going to remove from the domain. And then likely everything else will be included in the domain. So I'm going to take that denominator, set it equal to 0, and solve. And looking at that, well, I can see that negative 9 will cause the left side of this to be 0. And if you do a little bit of algebra, you'll get 3/4 for the other factor. That won't cause that one to be 0. So these two values make the denominator 0, which means they cannot be in the domain for this function. There's no other values that, if I plug them into this equation, will give me problems. So everything else is in the domain. So I'm going to write the domain as, well, everything to the left of 9, negative 9, everything between negative 9 and 3/4, and everything to the right of 3/4 on the number line. So I end up with these 3 intervals added together using my union symbol. And sometimes it helps just to write them on a number line or plug in the graph of the function. Now the domain or the range is a little bit harder to come up with from just looking at it, but especially because I have an x on the top, I should be able to get any value out of this. It is nice though to always look at the graph itself to kind of confirm any suspicions you have. So let's go ahead and take a look at the graph of this. I'm going to pull up Desmos. If you haven't used Desmos, it is great. And I'm going to type in, sorry, that's for later. I'm going to type in the equation. So if you haven't had a lot of experience, you can watch me type in this equation. I'm going to go y equals, just as it was written. And then I've got the 6x divided by, so I'm using the slash on my keyboard. And then I'm going to type it just how it was written. So 4x minus 3 in parentheses, and then x plus 9 in parentheses. And here I can see my function. And I can see some weird stuff happening at the places that I predicted when I found the domain. Here's 3/4. I've got something weird going on there. And out here at negative 9 also. Those are my undefined spots. This is what happens on the graph when you have a rational function that at the points where the denominator is 0. But looking at these graphs, and I can even zoom out if I want on them. If I go look vertically along the y-axis, well, they go up forever, they go down forever. And even at the origin, even though it looks like I have a line here that's approaching 0, right here, I do actually hit 0 in the middle. So I can get any value in the range, and this kind of confirmed that for me. So my domain is negative infinity to infinity. It's everything for this one. The next one is a radical. I have a square root in there. And with these, the issue that I run into is I can't take the square root of a negative number without having to deal with imaginary numbers. And when we're talking about the rectangular coordinate system, we are only looking at real numbers. So anytime I might get an imaginary number is when that something is not going to be in the domain. So here the radicand is what we call the inside of a radical. So that 2x plus 6, if that's negative, well, then that's not a real number and it's not in the domain of the function. So what I can do is take that 2x plus 6 and find out when is it greater than or equal to 0. Those are okay. If it's positive or equal to 0, I'm okay. So if I just solve this, I'll subtract 6 from both sides and then divide by 2. So I get x is greater than or equal to negative 3. Now that's the only place in the domain where I should have an issue is anything that is less than negative 3. So everything to the left. So my domain is going to be negative 3 all the way to infinity. Anything bigger than negative 3 is in my domain. Now for the range, this one, again, I always find it reassuring or at least helpful to look at the graph. So let's look at the graph of this one as well. So I'm going to clear out the last function and start over. So y equals, and I like to just type this. So the abbreviation for square root that this will identify is SQRT, and it switches it to square root when I do that. And then I'll just type in there 2x plus 6. Okay, so it's confirming for me, if I grab and drag this, it's confirming for me that there's nothing to the left of negative 3. So my range is negative 3 to infinity. And I can also see that, and this makes sense thinking about the equation, I can't get a negative number from square rooting either. The square root of any positive or zero value or 0 is going to be positive as well. So I should never get anything below the x-axis out of this function. So the range starts at 0 and it goes up to infinity. So my range here is 0 to infinity. And you notice I use brackets on both of these because they are included. It is okay to get 0 from this one. Okay, so that's how you can figure out the domain and range from looking at the equations and the graphs. The other thing we want to talk about in this section is piecewise defined functions. A piecewise defined function is a function in which more than one formula is used to define your outputs. So these look a little weird. They took a little getting used to the notation and how to interpret it. But a nice way to kind of think about these or start thinking about piecewise defined functions is by looking at the absolute value function. So we've seen that the absolute value of x gives me this nice V shape. And I can actually define this as a piecewise defined function. Okay, the absolute value is a nice convenient way of writing it, but I can split this up. Think of this as, it looks like I have one line going down to the left, to the right, sorry, and another one going down to the left, and they kind of meet at that point. So they look like really two distinct lines, and I could come up with an equation for each one of those lines. It's just that, the rule ends when we hit 0 for each one of them. So if I plug in a negative value, I get the positive version of that number. So the absolute value of -1 is 1. And then same thing for the right side. If I plug in a positive value, I get the same value out. So it looks like this. For any value that's greater than or equal to 0, the output is the same as the input. If it's a negative, so any value that's less than 0, then I just get the opposite of it, the opposite sign. And so this is one way of describing a piecewise defined function, where I've got one expression for positive values and 0, and another expression for the negative values. So each one of these there's a line for the output expression, and then the condition under which you would use that particular expression. So everything should be defined that's in your domain and range when you're looking at these. And then we collect them and kind of keep them together using that curly bracket to the left. Okay, so let's look at an example. We can really go crazy with these and start mashing any combination of functions together and just pick when one ends and the next begins. So here's an example where I have 3 expressions. I'm breaking up my interval to everything less than 0, everything from 0 to 3, and everything greater than 3. Okay, so I'm going to practice evaluating this for a few different values. Then we'll look at the graph and we'll see if we can come up with the domain and range as well. Okay, so f of 0. Okay, so my x value is 0. And if I look at my conditional statements after each of my expressions, well, the middle one is the one I would use when x is 0. So f of 0 is 3. If I look at x equals negative 3, well, that would be the first expression because that's something that's less than 0. So I would use 5x. So f of negative 3 would be 5 times negative 3, which is negative 15. And the last one, f of 5. Well, 5 falls under the third expression because it is greater than 3. So I would plug that into the expression x squared. So f of 5 equals 5 squared, which equals 25. Okay, so very different answer that I get and calculation I do depending on what the input is and those conditional statements off to the side. Okay, if you're wondering how to graph this, well, you take it an interval at a time. You can do this using a table where you start, where you start plugging in values that are less than 0 and get an idea of what the graph looks like for those values, then plug in some values from 0 to 3, and then see what that piece looks like, and then for the third one as well. If you're wondering, well, how in the world can I do this in Desmos? Well, that one I already have typed up because I figured you didn't want to watch me type it all in, but you can look very closely on the left here at my equations to see how I typed in the equation, and this is what we end up getting. So the first one, you put the condition first, and then a colon, and then the expression, all in curly brackets. And you do that for each one. And the dots don't show up, so you have to just label those as, you have to identify where they should show up based on where your or equal to inequality is, which in this one, it was in the middle one where f of x equals 3. And you just plot those points. So you get solid dots here. There should be circles here. So I can see for everything less than 0, I get the line for y equals 5x. And then once we hit 0, it jumps to the middle one, which is this horizontal line at f of x equals 3. And then when we get bigger than 3, it jumps up here to the x squared function. And we can zoom out a little bit if you want to see a little bit more what that looks like from far away. Okay, so from looking at this, the domain, well, it looks like, no matter what value I can think of, I will have an expression to plug it into. All x values fall into one of these. I don't end up with an undefined or a non-real number or anything like that anywhere. So the domain is going to be everything from negative infinity to infinity. Range, not so much though. You'll notice there are some gaps. If we start zooming in some more, it goes from 0 and then it jumps up to 3, and there's no graph anywhere in between when I look vertically. And same thing from 3 up here to, looks like that's 9. Yeah. So those chunks are not part of my my range. I'll never be able to get a value out because there's no graph there. So it's going to be from negative infinity to 0 along the y-axis, and then just at x equals 3, and then from 9 to infinity. So if you want to see what that looks like, the domain's everything, negative infinity to infinity, and the range is going to be negative infinity to 0, and I did not include 0 in that, and then 3 to 3, and then 9 to infinity would be my range. Okay, that's how piecewise defined functions behave. So there's a couple examples under this video for you to try this out on your own.